Last time, Cholesky decomposition wrote a symmetric positive definite matrix as L times L transpose. Today, the same factorization becomes a random number machine. Linear algebra found a side job. For this video, a random number is just a machine that spits out numbers according to a distribution. We assume we can ask for independent standard Gaussian numbers, called Z1, Z2, and so on. Standard Gaussian means mean 0 and variance 1. No measure theory today. The monster can remain under the bed. Suppose we are given a mean vector mu and a covariance matrix sigma. We assume sigma is not singular. So in this video it is symmetric positive definite. The goal is to create random numbers whose average is controlled by mu, and whose covariance is controlled by sigma. In other words, we want randomness with instructions, because apparently even chaos needs paperwork. Take the Cholesky decomposition of sigma. So sigma equals L times L transpose, where L is lower triangular. Now collect independent standard Gaussian numbers into a column vector Z. The mean of Z is 0, and the covariance of Z is the identity matrix. Then define X equals mu plus L times Z. That is the whole algorithm. Beautifully short, which is suspicious, but correct. We use one basic probability fact. A linear combination of independent Gaussian random numbers is still Gaussian. We are not proving that here. Probability theory may file a complaint. Each coordinate of L times Z is a linear combination of Z1 through Zn. So each coordinate is Gaussian. Adding mu only shifts the center. It does not destroy Gaussian behavior. For once, addition behaves like a responsible adult. The mean calculation is direct. The expected value of X equals the expected value of mu plus L times Z, which equals mu plus L times 0, which equals mu. So the mean vector does exactly what its name promises. A rare moment of honest branding. For covariance, subtract the mean. Since X minus mu equals L times Z, the random part is exactly L times Z. Covariance of L times Z is L times covariance of Z times L transpose. Since covariance of Z is the identity, we get L times L transpose, which is sigma. Here is a two-dimensional example. The mean is 10,5, and the covariance matrix has positive off-diagonal entries. A Cholesky factor is L equals the matrix with rows 2, 0, and 0.6, 0.8. Multiplying L by L transpose gives the covariance matrix. To generate one sample, take two independent standard Gaussian numbers. Put them in Z, multiply by L, and add the mean vector. Notice that both coordinates contain Z1. That shared random ingredient creates positive covariance. Random numbers. Now with teamwork, humanity is doomed. Before multiplying by L, the independent Z cloud has no preferred tilted direction. It is just standard Gaussian noise behaving politely. After multiplying by L, the cloud is stretched and tilted. That shape is the covariance matrix showing up on screen instead of hiding inside a formula like a coward. So the algorithm is simple. Compute the Cholesky factor, generate independent standard Gaussian numbers, and return X equals mu plus L times Z. The output has the requested mean and covariance. The assumption that sigma is non-singular keeps ordinary Cholesky decomposition happy, which is more than we can say for most software. Next time. We move to polar decomposition, where a matrix splits into a rotation-like part and a positive part. Because apparently matrices also want a personality breakdown.